What we had done in the previous example was bias the amplifier by fixing VGS at 1.816 volts. However, this is not a good biasing technique. To understand that, let's first recap the definition of biasing. Biasing is the establishment of an appropriate and reliable DC operating point for the device. The DC operating point is characterized by a stable and predictable DC drain current ID and a DC drain voltage VD. This ensures operation in saturation region for all expected input levels. What we were doing was that we had fixed VGS. It could have been provided from a DC supply voltage VDD by the use of an appropriate voltage divider or derived from another suitable reference voltage. Either way, the current ID would have the equation ID equals half mu n C oxide WRL VGS minus VT whole squared. The threshold voltage VT, the oxide capacitance Cox, the transistor aspect ratio WOL vary widely among devices of supposedly the same size and type. This is the case for both discrete devices and also for integrated circuits. Also, both the threshold voltage VT and mu n depend on temperature, with the result that if you fix the value of VGS, the drain current ID would become temperature dependent. Why? Because no other factors apart from VGS provide the desired current ID. Let me demonstrate that to you further. Look at the graph on your bottom right. The two ID VGS characteristic curves represent extreme values in a single batch of MOSFETs of the same type. Note that for the fixed value of VGS, the resultant difference in the values of the drain current is very large. In other words, the same circuit employing two different devices of the same batch in two different instances of time will not produce the same drain current. That is why we do not fix VGS. In the upcoming lessons, we are going to study techniques that do provide reliable biasing.